Hello, this lab lecture will involve discussing experiment 7, synthesis of aspirin. So I'll go over some of the topics that you should read about for this experiment, and remember to do the pre-lab quiz and post-lab questions for experiment 7 on Blackboard, and the virtual lab for experiment 7 will open up next week on Monday at 8 a.m. So next week, we would have been performing the experiment synthesis of aspirin. So again, for experiment 7 on Blackboard, make sure you do the pre-lab quiz, and which is due by 11:30 p.m. this Sunday, and then you will need to do the post-lab questions for experiment 7 when they open this following Monday. And so the reason that students do the synthesis of aspirin lab is this incorporates an area of chemistry called organic chemistry. In organic chemistry, what we're doing is we're changing certain groups on the molecules to make new molecules with different chemical and physical properties. So organic chemistry, as you'll learn about later on if you take organic chemistry in future semesters, is that it deals with compounds that contain a lot of carbon and hydrogens. So organic chemistry is the chemistry of carbon compounds. Now, depending on what types of atoms, in addition to the carbon and the hydrogens they usually have certain chemical and physical characteristics. And so based on these generalized groups of organic compounds, you can predict what type of reactions will occur. For example, if you have an alcohol, for example, it can undergo a reaction where it forms a ketone. So you can oxidize an alcohol to a ketone. And in addition to carbon and hydrogen atoms, we have other types of what we call heteroatoms. So oxygen, nitrogen, sulfur, etc., these are referred to as heteroatoms. And so all organic compounds have what we call a hydrocarbon skeleton. So it has this big backbone of carbon and hydrogen atoms, but it can also have other types of heteroatoms. Some common ones are oxygen, nitrogen, sulfur. Generally, these are other non-metal elements. And so based on the number of carbon and the type of bonds in the backbones, types of bonds in the backbones, we can determine the name of the compounds. So for example, in this first one, you see that there are only 2 carbons attached in the backbone, in this hydrocarbon. So whenever there's just 2 carbons attached in the backbone, we use the prefix F. And these 2 carbons are connected by only single bonds. So then we use the suffix -ane. So this compound is called ethane. F for the 2 carbons, ane for the single bond. Now if we go to the next example, here we have 3 carbons in the backbone. So for 3, we use the prefix -prop. And they're all connected by single bonds. So we use the suffix -ane. So this is propane. For organic compounds, the prefixes 1 through 4 are a little bit different than what is used in general chemistry for naming covalent compounds. But once you get after 4, they're pretty much the same as the naming the prefixes we use for naming for regular binary covalent compounds. Now in the next example, we have 4 carbon atoms. So since it's 4, we have to use the prefix but. But then you'll notice here that after the first carbon atom, we have a double bond. So since you have at least one double bond, since you have one double bond in the chain, we have to use the suffix -ene. So now we have butene. And if we look at the second example next to it, again, we have 4 carbon atoms, which is but, and we have one double bond, which is -ene. So both of these are called butene. So the way we distinguish these two compounds is identifying after which carbon the double bond comes after. And so for the first example, it comes after the first carbon. So this would be called 1-butene. And you always go from the shortest side. So there's no such thing as 3-butene. It's only 1-butene, because again, you got to go to the shortest side, count from the shortest side. In the second example, 1-2, the double bond comes after the second carbon. So that's where the 2 comes from. So 1-butene and 2-butene are different compounds with different types of chemical and physical properties. And so, for example, here we have 4 carbons again. We use the prefix but, but since they're all single bonds, we use the suffix -ane. So when you have double or triple bonds, you have to include, if it's a 4 carbon chain or greater, you have to include the carbon, the number of the carbon, where the double or triple bond comes after. Next, we have a compound that is branched. And so again, for branch compounds, you first look at the part that's the longest chain. So this is the longest continuous carbon chain here. So this is 3 carbons. So we use the prefix pro. And all 3 of these carbons are connected with a single bond. So we use -ane. So we have propane. And you'll notice after the second carbon, or on the second carbon, we have a methyl group attached to it. So since the methyl group is attached to the second carbon, we would say 2-methyl propane, which is commonly referred to as isobutane. Another type of compound we can have in organic chemistry are ring compounds, so compounds that form a ring. So here, for example, if we look at this ring, we see it has 6 carbon atoms. So 6, again, we use the prefix hex. And all of these carbon atoms are connected with single bonds, so we use the suffix -ane. But notice that these 6 carbon atoms form a ring. And since it forms a ring, we use the prefix cyclo. So cyclohexane is a 6-membered ring that is only connected with single bonds between the carbons. Now, for example, if I was to put a double bond say I put a double bond here, since there's one double bond, you could say this is cyclohexene because there's one double bond here. If there was a double bond there, it would be called cyclohexane. Cyclohexene. Ene is used for double bonds. Ine is used for triple bonds. And since it's cyclo, you don't have, since there's only one double bond, you don't have to put one cyclohexene. You can just put cyclohexene. Now the last example is a 6-membered ring that has alternating double bonds. And this is a special group of compounds that have this ring in it. And this ring is called a benzene ring. So a benzene ring is a 6-membered ring with alternating double bonds. So every other carbon has a double bond. And this is a unique organic compound or organic motif that's used a lot and has a very special class of compounds that contain this ring. So compounds that contain this ring or similar to this ring are referred to as aromatic compounds. And again, this is just an introduction. When you take organic chemistry, you'll learn a lot more about naming. And so on these carbon backbones, what we like to add to them are what we call functional groups. So functional groups are groups we add to the carbon backbone to give it certain chemical and physical properties. And so when we're looking at these groups, you'll notice that on one end of the group, I put an R. So R just refers to the rest of the structure. So again, R is just the rest of the molecule. So for example, for the first type of functional group that we see is a alcohol group. So an alcohol group is an oxygen atom bonded to a hydrogen atom. So you have what's called an OH group. So when you have an OH group attached to a molecule, it's referred to as a alcohol. So let me see if I can draw one for you. So for example, this would be an alcohol. This is actually 1, 2, 3. This is propanol. So again, what you're looking for is this OH attached to the rest of the molecule. That's referred to as an alcohol. Some of you even consume an alcohol called ethanol. I'll show you that. So ethanol is this. So this is called ethanol. All is used for alcohols, and since you have 2 carbons, it's referred to as ethanol. This one is called propanol because it has 3 carbons and an OH group. So alcohol is one type of functional group you can add to these carbon backbones. The next type of functional group we're going to talk about is an aldehyde functional group. And so an aldehyde functional group is always at the end of a carbon chain. It can't be in the middle because it has what we call a carbonyl group, which is a C double bond O and an H. So this is the unique component for an aldehyde. So using the alcohol example, if we were to make that propanol into an aldehyde, propanol, I believe is the correct term. So we go 1, 2, it would look something like this. So now notice the difference between the alcohol and the aldehyde. The aldehyde has this group at the end. And aldehydes and alcohols have different chemical and physical properties. Now, a cousin of aldehyde is called a ketone. And so the only difference between an aldehyde and a ketone is that instead of an H that we have for aldehyde, we replace it with an R. And so the key thing about a ketone, and again, ketones can only occur, or the ketone functional group, the carbonyl group, can only occur in the middle of a carbon backbone, because on both sides of the carbonyl, you got to have an R group. So this is the key identifier of a ketone. You have a double bond oxygen that is surrounded by two R's. So now if we were to take our example of propanol and turn it into, make it look like a ketone, it would look something like this. And so that would be a ketone, because here you have one R group, and here you have a second R group. And the R's do not have to be the same. They can be different. So if we were to, for example, make this longer, then it would be the same. It's still a ketone. It's just a bigger R group. Now again, I may not have mentioned it earlier, but what I'm drawing is called the skeletal structure for organic compounds, because it's very tedious to write the Lewis structure of these organic compounds. So again, what I write is called the skeletal structure. And the skeletal structure just shows the carbon backbone without any carbon or hydrogens and any heteroatoms. So again, since we're dealing with a skeletal structure, what you have to remember is that carbon likes 4 bonds. So whenever carbon doesn't have 4 sticks around it, it's understood that hydrogens make up the difference. So for example, here at the end of this chain, there's only one line for that carbon, which means there's 3 hydrogens that is understood that is attached to it. Here we have 2 lines, or an intersection, and since there's 2 lines or 2 bonds of this carbon, it's understood that the other 2 are made up of hydrogens. So for organic compounds, we don't show all the carbon and hydrogens. We just show the backbone and then the heteroatoms. So for example, here this carbon atom has 4 bonds, so there's no hydrogens attached to it. So again, what you have to remember is that carbon likes 4 bonds. If it doesn't have 4 bonds attached to it, that means that the difference is made up with hydrogen atoms. One of my colleagues is an organic professor, and she says the way to remember this is that a cat has 4 legs, so carbon has to have 4 bonds. She actually has a cat named Carbon. So again, down here at the bottom, this carbon has 2 bonds, so that means that the other 2 are hydrogen atoms. And this is the shorthand way, or the skeletal structure, that we use to draw organic compounds. Now, a cousin of alcohol is what we call the ether functional group. And again, an ether group has to occur in the middle of a molecule, because you'll notice for an ether, which is a little bit different than an alcohol, an ether has 2 R groups attached to it. And these may or may not be the same. And so what you're looking for is an oxygen that has single bonds the two R groups. This is called an ether. So an example of an ether would be something like this. So again, you have your single bond oxygen, and it's connected to two R groups. So this would be an ether. And by the way, for organic compounds, oxygen is going to undertake one of two forms most of the time. It's either going to have two single bonds or one double bond attached to it. Now, when we take, say, an ether and cross it with a ketone, we get what's called a ester. And so an ester has this unique component in it, the C double bond O group. And esters, the ester group has to appear somewhere in the backbone. It can't appear at the end. So if we were to take this ether and show you what an ester looks like, it would look like this. And I apologize, it's my drawing is a little bit wonky. See if I can get it right this time. No. Yeah. And so this would be an ester. Because again, what you're looking for is this C double bond O group. So this is the ester group. And again, esters occur, the ester group occurs somewhere in the carbon backbone. It cannot occur at the end. Because if it occurs at the end, it's a different type of functional group, which is referred to as a carboxylic acid. And so the last group we're going to discuss is a carboxylic acid functional group. And this occurs at the end of a carbon backbone. And so it has a C double bond OH group. So very similar to an ester, maybe the brother of an ester. So the only difference is for a carboxylic acid, we have a H instead of an R. So esters have an R attached to the single bond oxygen. Carboxylic acids have a H. And so now if we were to take this ester that we've drawn and show you what a carboxylic acid looks like. This would be a carboxylic acid. This is actually called propanoic acid. So again, for carboxylic acid, it occurs at the end of the carbon backbone or carbon chain and has this C double bond OH group. And so the main objective of learning about these functional groups is, can you identify the functional group when given a molecule? So that's what you'll be looking for in this exercise. And so what we would have done in lab is we're going to take a carboxylic acid and actually convert it to an ester. And that's what happens in the synthesis of aspirin. The reactant we use is a carboxylic acid. It undergoes a reaction, and then we form an ester, which is what aspirin is. And so the precursor that we're using for the experiment, or what we would have used, is salicylic acid. And it was originally found in the bark of willow trees. So the bark and the leaves. So people used to, chew on the bark or the leaves, and they would get this salicylic acid. It was first reported in the ancient Greek times. Hippocrates reported the usage in around 400 BC, and even then it was used to relieve pain and fever. So notice the precursor and aspirin itself, acetylsalicylic acid. Again, salicylic acid, the precursor, has been used in the medicinal properties for thousands of years. However, next week when we talk about acetaminophen, it has a different history. And so it wasn't until the 1800s that they isolated the active component in the willow bark, which was salicin. And they noticed that salicylic acid was very harsh on the stomach, caused tummy aches. Oops, let's get rid of that. And so they converted it to acetylsalicylic acid, which is the present day aspirin that we use. So next, or if we were to do this in the lab, we would have started with salicylic acid and converted it to acetylsalicylic acid. So the reaction that we would have done to produce acetylsalicylic acid is called an esterification reaction. What we do is we convert a carboxylic acid into an ester. So again, a carboxylic acid has a C double bond OOH group. We react it with an alcohol, and this is called an acid catalyzed reaction. So what this means is a catalyst is used to speed up the reaction, because if you don't use the catalyst, it may take a long time for the reaction to occur. So we use an acid catalyzed reaction. From the equation, the way we know this is an acid catalyzed reaction, because HCl is written here, means that this reaction is done in an acidic environment. And then we produce our ester, which has a C double bond O OR group. So we go from an acid to an ester. An example of this, we take benzoic acid. Again, it has a C double bond OOH group. We react it with ethanol, which is our alcohol. H plus above the arrow signifies it's in acidic conditions. And we produce our ester, C double bond O, with two R's on both sides. So the ester is named ethyl benzoate. And then we have another byproduct, water. So again, we take a carboxylic acid, react it with an alcohol in an acidic solution, and we form a ester. So with salicylic acid, what we're going to be, for the esterification of salicylic acid, we're going to start with salicylic acid, which has a carboxylic group here. And we're going to react it with another compound called acetic anhydride. And acetic anhydride has something called a acetyl group on it. And the acetic anhydride is going to react with salicylic acid to form acetylsalicylic acid and a byproduct, acetic acid. The official name of salicylic acid is ortho hydroxybenzoic acid. And it's a bifunctional compound. Bifunctional means it has two functional groups on the compound. So we talked about the carboxylate group here, but also salicylic acid has an OH group. And when an OH group is directly attached to a benzene ring, it's usually referred to as a phenol. So we have an alcohol component and an acid component on the salicylic acid. And so salicylic acid by itself has the ability to undergo two different types of esterification reactions. It can act either as the alcohol or as the acid. And from this, we see that salicylic acid is acting as the acid, acting as the alcohol, and acetic anhydride is acting as the acid. So it's the OH group on salicylic acid that reacts with the acetic anhydride to form acetyl salicylic acid. So again, salicylic acid acts as the alcohol. Acetic anhydride behaves as if it was a carboxylic acid. So something about the impurities for this type of reaction. The main impurities are easily to detect. One of the common impurities is, of course, salicylic acid. Maybe your reaction didn't go to 100%. And so the way we test for salicylic acid is you would do what's called a ferric chloride test. And what a ferric chloride test does is when you add ferric chloride to a solution that contains a phenol, it produces a very vibrant color, usually anywhere from red to violet color solution. So if you were to test your product and when you added the ferric chloride, it changed color, that indicates that you have some salicylic acid impurity left in it. Now, aspirin won't react with ferric chloride because aspirin has no hydroxyl group. So there's no hydroxyl group in aspirin. So if your ferric chloride solution changes color when you add your product, that indicates that you have some salicylic acid left in the solution. Another main impurity is acetic acid, and this one's a very odorous impurity. So when your reaction is occurring, you would actually get you would smell the scent of vinegar, which is acetic acid. That indicates that the reaction is occurring because you're producing acetic acid, and it's very water soluble. And this is a very common main impurity in this type of reaction. And the best way to remove the acetic acid is by washing it several times with cold water. So you would wash it, you would waft to see if you smell the scent of acetic acid. If you do, keep on washing until no more scent is there. Because this is a very common impurity which messes up the product acetic acid. So when you make aspirin, acetic acid is a big byproduct of this reaction. Now, one way we would determine the presence or that we have made your acetyl salicylic acid is by using a technique called IR spectrophotometry. And IR utilizes a particular energy of a molecule. So the energy of a molecule is made up of three types of energy: electronic energy, which we'll talk about more in experiments 9 and 10, which electronic energy utilizes UV vis spectroscopy. We have vibrational energy and rotational energy. So IR spectrometry deals with the vibrational energy of molecules. So what we're going to be looking at with IR spectrometry is the vibrational energy within the bonds of molecules. And so what happens is in the IR infrared region, molecules vibrate at certain frequencies. And so based on the type of bonds you have in your molecules, they give different what we call vibrational frequencies. And so from that, you can determine the types of functional groups in your compound based on how those bonds vibrate. And they give certain frequencies for it. And so this is one of the ways we would use to confirm that we have acetylsalicylic acid is by using IR spectroscopy. And it uses the vibrational energy of a molecule. There are many different types of vibrations. The bonds can stretch. They can stretch symmetrically. They can stretch asymmetrically. So symmetric stretching means they both go in the same direction. Asymmetric means as one comes in, the other one goes out, kind of like you're hitting two balls, and as one ball hits the middle ball, the other ball goes out. So these are types of vibrations that occur. So the bond stretches either symmetrically or asymmetrically. The bonds bend. So you have different types of bendings, and all of these give off frequent vibrations in the IR region. So if you had a detector that could detect IR frequencies, you can detect where these bonds bend and stretch. Again, we're just introducing the concept IR spectroscopy. If you take organic chemistry, you'll learn a lot more about it, and especially if you take upper level chemistry courses. So this is an example of an IR spectrum. So what you would have done is once you obtained your product, you go get an IR spectrum and compare it to the IR spectrum of known acetylsalicylic acid and see if the two match up. So for example, here, this frequency at 2971 wave numbers. So again, in IR, we deal with wave numbers. That's the x-axis. Which is centimeter inverse. So based on this compound, we had a frequency at 2,971, which means it's the OH bond is stretching and the CH bonds are stretching. So this tells you that this compound has a OH stretch and a CH stretch. At 1721 is characteristic for carbonyls. So you have this C double bond O stretching here. And this is, again, this compound is hexanoic acid. So here's the CO group. Here's the CH group. Then we have the OH bending and CO bending at 1419, 1296. And then the OH, another type of OH bending as well. So usually with our spectrum, you want to note the very strong frequencies. You don't have to note every little frequency, but the main frequencies that show up in the spectrum. Probably the only type of calculation that you do in organic lab is a percent yield calculation. And so just to kind of go over percent yield for this type of problem, we have 5 grams of salicylic acid. We reacted with 15 milliliters of acetic anhydride. So the acetic anhydride is actually a liquid. And we give you the density. We produce 4.75 grams of acetylsalicylic acid. What's the percent yield of the reaction? So one of the first things you need, of course, is the molar masses of each reactant and product. First, we find moles of each reactant, so moles of salicylic acid, moles of acetic anhydride. Notice that for acetic anhydride, we got to convert it first to mass and then to moles because it's a liquid. Now, one of the neat things about organic reactions is typically they're 1-to-1 ratio. So 1 mole of salicylic acid produces 1 mole of acetylsalicylic acid. 1 mole of acetic anhydride produces 1 mole of acetyl salicylic acid. So they're both 1-to-1 mole ratios. So now we can find the moles of acetylsalicylic acid. And in this example, salicylic acid is the limiting reagent. So from that, we can get the theoretical yield. So in this case, theoretical yield is 6.48 grams. That's the theoretical yield. And now using that and the percent yield, or the actual yield, which was 4.75, this is the actual yield, we can calculate the percent yield. So in this case, the percent yield is about 73%, which is not bad for a known reaction. Typically, you want, between 70 and 100% is good for reactions that are well known, so reactions you do in the lab. And this is the only calculation you would do for this type of experiment, because you just want to calculate the percent yield. So just some summaries here. Make sure you complete the pre-lab quiz for experiment 7 by the due date this Sunday, 11:30 p.m. You need to make it 60 or better to access experiment 7 post-lab questions, which will be open Monday morning. Post-lab report for experiment 5, the due date has been moved to Monday, March 30th, 5 p.m. Post-lab questions for experiment 6 due Sunday at 11:30 p.m. and the experiment 6 virtual connect lab is due at this Sunday, 11:30 p.m. as well. So make sure you do these assignments. Again, I sent out the email about the access code for the Connect labs. So make sure you click on that, register, and start working on the experiment 6 virtual lab. So that's all we have for today. On that note, we'll see you next time.